This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2019 AP Calculus exam, free response question BC6, namely Taylor series and e to the x. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. This will be a very general introduction to Taylor series, followed by a focus on the Taylor series, or really the Maclarin series, for e to the x. I'll begin with just a quick review, or rather a few conclusions about power series. And then I'll develop or construct the general Taylor series for a function, and then define a special case, a Maclarin series. And then I'm going to focus on the important Maclarin series for e to the x. I'll introduce Taylor polynomials associated with e to the x, and talk about approximating a function using Taylor polynomials, and how to visualize this concept. And finally, I'll leave you with several typical questions, AP Calculus type questions, for you to try. I'm going to assume that you have already concluded a study of power series, radius and interval of convergence, and finding new power series from old using algebraic manipulation, differentiation, and integration. In this presentation, I'm going to think about which functions actually have power series representations, and how can we find these representations. To determine whether a function has a power series representation, let's start by working backward. Now, this seems a little weird, but let's suppose that f is any function that can be represented by a power series. And let's see if we can figure out what it would look like in terms of the original function f. Now, I didn't write this down, but let's assume there is a radius of convergence r. And just as a reminder, this is called a power series in x minus a, or a power series centered at a, or a power series about a. So let's try to determine what the coefficients c sub n must be in terms of the function f. So first notice that if we let x equal a in this equation for f, then all of the terms after the first one are 0. And we get that f of a is equal to c sub 0. Well, that seems like a good start. Let's continue our search for the nature of these coefficients. Now we assume that the power series has a radius of convergence r. So we can differentiate this power series, arrive at another power series with same radius of convergence. So here's an expression for f prime of x. Again, let's let x equal a, and we find that f prime of a is equal to c sub 1. I'm looking for a pattern here. I don't quite see one yet. Well, let's try this one more time. Differentiate again. Let x equal a, and we find that f double prime of a is equal to 2 times c sub 2. Well, I gotta try this one more time. I can't quite see the pattern emerging. Here's f triple prime of x. Let x equal a, and we find that f triple prime of a is 2 times 3 times c sub 3. Or another way to write this is 3 factorial times c sub 3. By now, hopefully, you can recognize a pattern. If we continue to differentiate and let x equal a, we obtain the nth derivative of f evaluated at a is equal to 2 times 3 times 4, all the way down the line, times n, times c sub n. And another way to write this is n factorial times c sub n. So next, solve this equation for the nth coefficient. And we can find that c sub n is equal to the nth derivative of f evaluated at a divided by n factorial. And note that this formula is valid even for n equals 0. because we can use the conventions that 0 factorial is equal to 1, and the 0th derivative of f is just f. Now, this derivation proves the following theorem. It says that if f has a power series representation at A, that is, if f can be written this way, then its coefficients are given by this formula, the one that we just derived. So let's try to put some of these results together to connect the ideas of power series and Taylor series. First, if we use the formula for C sub n, then if f has a power series expansion at A, then it must look like this. This expression is called the Taylor series of the function f at A, or about A, or centered at A. And for the special case when A is equal to 0, the Taylor series becomes this expression. And this is called the Maclarin series for f. Here is just a quick, closer look at the previous argument, because I think it's tricky. If f can be represented as a power series about A, then f is equal to the sum of its Taylor series. However, there are functions that are not equal to the sum of their Taylor series. I wonder if you can find one. Well, let's try an example. Find the Maclarin series of the function f of x equal e to the x, and while we're here, its radius of convergence. Well, since the nth derivative of e to the x is e to the x, then the nth derivative evaluated at 0 is equal to 1 for all n. So we use this result and the formula for a Maclarin series. And here's the Maclarin series for e to the x. To find the radius of convergence, make use of the ratio test. Here's the absolute value of the ratio a sub n plus 1 over a sub n. And here's the limit, which is 0 for all values of x. Therefore, the radius of convergence is infinity, and the Maclarin series converges to e to the x for all values of x. So, our conclusion from the previous theorem and this example is the following. If e to the x has a power series expansion at 0, then darn it, we found it. However, we need to determine whether e to the x really does have a power series representation. Now, this leads to a more general question. Under what circumstances or conditions is a function equal to the sum of its Taylor series? Or another way to think about this, if f has derivatives of all orders, when is it true that we can write f in this manner? So, how do we show that a function f is equal to its Taylor series? Well, if the Taylor series converges to f of x, then f of x is the limit of the sequence of partial sums. So it makes sense that we look more closely at the partial sums. Well, here's an expression of the nth partial sum, and this is called the nth degree Taylor polynomial of f at A. Let's take a look at some specific partial sums, or Taylor polynomials. If f of x is equal to e to the x, then the Taylor polynomials for n equal 1, 2, and 3 are shown here. And let's use a little technology also. The TI-Nspire has a built-in function called Taylor that will generate Taylor polynomials. For example, here's the third degree Taylor polynomial for e to the x about 0. Note that there is an optional fourth argument for this function, for a, which is by default 0. And here's the sixth degree Taylor polynomial for e to the x, about 0. The graphs of these three Taylor polynomials and of e to the x are shown in this figure. Notice that as n increases, the graph of t sub n of x, the nth degree Taylor polynomial, appears to approach the graph of e to the x. So this graph suggests that e to the x is equal to the sum of its Taylor series. Well, we all know that a graph isn't good enough. We need something more formal to show that e to the x is equal to its Taylor series. So, if f of x, in general, is the sum of its Taylor series, then f of x must be equal to the limit as n goes to infinity of t sub n of x, that is, the limit of its Taylor polynomials. Now, in order to evaluate this limit, we consider the remainder, and here's the definition. If we can somehow show that the remainder goes to 0 as n increases without bound, then f of x is equal to its Taylor series. And here's the theorem that states just that. Essentially, if the limit as n goes to infinity of r sub n of x is equal to 0, then f is equal to the sum of its Taylor series. In general, it's not an easy task to apply this theorem to show that the remainder term goes to 0. However, in order to prove this for a specific function, we often use Taylor's inequality. This provides a bound for the absolute value of the remainder. So I'm asking you to trust me on this one. We can indeed show that for e to the x, the remainder term goes to 0. And therefore, e to the x is equal to the sum of its Maclaurin series. Very cool. And finally, here are some typical AP Calculus type problems that involve Taylor series and Maclaurin series. These problems involve finding a Taylor series about a value different from 0, a consideration of a few more graphs to visualize the convergence, finding some new Maclaurin series from old Maclaurin series, and I think a cool application involving integration. I hope this video provides some background and insight into Taylor series, Maclaurin series, Taylor polynomials, the remainders, and examples for finding new series from old. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.